Hello, chemistry students. In this video, we're going to discuss the nature of energy, the different types of energy, and how a system can hold what's referred to internal energy and transfer that in the two forms of both heat and work. So even though chemistry is the study of matter, we have to realize in a lot of chemical reactions, energy is released or absorbed. For an example, we don't burn wood because we want ash. We burn wood because of the release of heat that it provides and it keeps us warm. So we have to also study energy when we study chem. So all forms of matter are associated with energy, and we can measure that as either heat or work. So work is a force acting over a distance. So force, you can think of force as it requires force to push, pull, or lift something. And to apply that force over a certain distance requires energy. And that's energy in the form of work. So it takes this man energy, work, to push and exert a force on this box and move it over a certain distance. Now, heat is a flow of energy caused by a difference in temperature. So energy can be exchanged between objects through contact. So for example, through collisions. So hotter objects or objects with more thermal energy move faster. When they collide with other objects that are moving slower, that transfers that thermal energy to the other object. So let's focus on energy, heat, and work. You can think of energy as a quantity that an object possesses. So I like to think of it, or a collection of objects, think of it as a system, or if you're looking at a particular reaction, the energy that the reactants have. So you can think of heat and work as the two different ways that an object can exchange energy with other objects. So if we're looking at a system, how the system can exchange heat or work on the surroundings, and we can look at it as work either being put into it or out of it, or heat coming into it or out of it. And when I say it, referring to the system or the reactants in a reaction. So there's two main types of energy. Okay, and remember, energy is the capacity to do work, which is force times distance. But there's kinetic energy, which a lot of people are familiar with. A lot of times you see kinetic energy written as KE for kinetic energy, and that's due to motion. Then there's potential energy, and that's sometimes written as PE for potential energy, and that's based on position when there are two bodies or two objects that have attractive force between them. They have a certain distance, and that's potential energy stored in that distance. So really, when we talk about chemistry, and we're talking about, very small particles, and we're looking at reactions, the kinetic energy really that we're looking at is thermal energy. And thermal energy is that heat energy, and thermal energy is either vibrational or movement of particles at a molecular level, and that's considered thermal energy or heat energy. And we typically can measure this with changes in temperature. Now, when you think of chemistry in the sense of potential energy, that's what you hear a lot of times referred to as chemical energy. And chemical energy is the energy that's stored in the bonds of reactants and products, really in all molecular structure. You have bonds which are made of electrons. Electrons are attracted to the nucleus, which have protons because they're oppositely charged. And based on the position of those electrons, because they're valence electrons, and their distance from the nucleus, they have different amounts of chemical energy, which again is potential energy based on distance. So the distance of the electrons from the nucleus is chemical energy. And in a reaction, we break bonds and make new ones. So now those relative distances of electrons from the nuclei have changed. So let's just kind of take a look at from a classical standpoint. Kinetic energy is motion, and the formula for this is 1/2 mv squared. M standing for mass, v standing for velocity. Velocity is a rate. A rate is usually distance over time. So in this particular example, we see that this billiard ball, this cue ball, has energy due to motion, so it is moving. As it collides with another ball, it transfers that internal energy to its surrounding, to the other ball. And now that energy transferred can be seen in the form of work. So the energy changes from the movement of this ball and through a collision transfers it so that it can do work on this surrounding ball. And now the surrounding ball has a force that's required to push it over a certain distance. So when we think of the units of mass and velocity squared, the units are kilograms, because those are typically the international system units that we use for mass. And for velocity, it's meters, which is a length, second, which is time, and we square it, so squared. And the units of kilogram meter squared per second squared is also referred to as a unit of joule. This is the most common unit that we use for measuring energy. We also use calories, but joule is the more common unit, and it's basically a kilogram per meter squared, or a kilogram meter squared per second squared. But an object at rest still has kinetic energy. So even when it's not moving, because the component atoms can vibrate. And that's typically what we refer to as thermal energy. As temperature rises or as it gets hot and the atoms absorb that thermal energy from the surroundings, they begin to vibrate more, and that's where we would see a temperature rise. So thermal energy is associated with temperature because we can measure temperature differences. Thermal energy is a form of kinetic energy because, again, it's movement. It's at a molecular level, but it's still movement and it's associated with kinetic energy. An object has more kinetic energy, really more thermal energy, which is basically heat when atoms vibrate more. So there is more heat in a system if the atoms are moving faster. And a good example of this is if your hands are cold, what do? You rub them together, you move them fast so they get hot. Now, we also said potential energy. So potential energy is stored in an object. So in this picture, I have a ball. It's attracted, to the ground, or in this case, the pool table, and there's the gravitational force pulling on it. So based on this distance, there's potential energy. As the ball is dropped, I lose potential energy because I'm gaining kinetic energy. So what's happening, I'm converting the position, the potential energy into movement, and I'm transforming it to kinetic energy. Now, kinetic energy, and you don't have to know these equations, I'm bringing them up. You might be familiar with them if you've taken physics, is mass times gravity times the height. Well, mass, again, is in kilograms. The gravitational pull acceleration of the Earth is 9.8 meters per second squared, and the height is measured in distance. And we see that also becomes kilograms meters squared divided by second squared, which is the unit of joules that we talked about earlier. So just like potential energy in a large scale, there is potential energy stored in all compounds based on the distance of the electrons, and we can make it easy, in orbitals based on the distance to the nuclei. And as the electrons are further out, further valence shell, there's more potential energy in that distance. So during a chemical reaction, energy is transformed, and we've seen this. So if light is released or absorbed, that's where there's a chemical change that's also associated with a change in energy and energy transformation, light being released or absorbed. We see that in combustion reactions. A great amount of energy is released, so it's released in the form of light. Heat being released and absorbed. Same concept. There's a difference in energy from reactants to products, so now the difference in energy is released as heat. The products become lower in energy, lower potential energy, so that difference in energy is released as heat. We see this in neutralization reactions. So when we combine acids and bases, they don't give off light, but there's enough energy where it's not as much as light, but it's releasing heat energy. Then there's thermal energy, again, which is associated with movement. Light is kind of a movement or transition of electrons from one energy level to another. We'll be learning that in the quantum mechanics chapter following this chapter on thermodynamics. Nuclear energy, well, that's potential energy found in the nucleus of atoms. And chemical energy, again, energy that's stored in the bonds of molecules and based on their positions. And when I have a chemical reaction, to go from reactants to products, the bonds have to be broken to form new bonds. And during that transition, there's a change in potential energy. So really, the last topic that I want to touch on is system and surroundings. So energy can be exchanged, as we said, between objects through contact. We define the system as what we're observing. So we typically pick one thing to look at, observe it, and then we look at the changes in energy within that system. So an internal energy. So typically when we refer to systems, we are referring to the reaction that we're observing in chemistry. We define the surroundings as everything else, and with the system comes in contact with or releases energy into or takes from. So in a combustion reaction, right, the actual reactants, the wood and the oxygen, would be the reaction, the system, and them undergoing a chemical change to produce CO2 and water. While they do that, the change in the system releases energy to the surroundings. So the combustion of wood, the burning of wood releases heat to the surroundings and warms the house up. So we see here that the man, right, he is pushing on this system. So he is applying work to this system so that it can move. So what we study in exchange of energy between the system and surroundings is typically referred to as thermodynamics or thermochemistry. We are observing energy changes within a reaction, and a lot of times we do this by measuring the energy changes in the surroundings. Now, I want to finish up with this video with kind of touching on the first law of thermodynamics and the law of conservation of energy. So even though we're studying energy and its interconversions between the system and the surroundings, also between potential energy, kinetic energy, and heat and work, the law of conservation of energy states that you cannot create it or destroy it. You can merely transform it. So that's kind of what we're looking at. We're looking at energy can be changed from one form to another or transferred from one object, let's say the system, to another, the surroundings. And I'll leave it at this, where I have a system, I have an iron bar here or anvil, it has a certain mass, it has a certain amount of potential energy based on the distance, because between this object, the anvil, and the earth, there's an attractive force, gravitational force, just like there's an attractive force between protons and electrons. So this distance is potential energy. When it falls, I'm losing potential energy in the form of distance. However, I am transforming that distance into kinetic energy, which is motion, because now it's moving from here to here. Even after it's traveled the complete distance, right? this system still has energy, and that energy is a form of kinetic energy. Now, it's not moving on a grand scale, but at a small scale inside the anvil, the molecules or particles are vibrating, and that's referred to the thermal energy that we discussed earlier. So I hope this video was helpful in understanding the nature of energy and how we can't create or destroy it, we can only transfer it, and how in thermodynamics we'll be studying systems by observing heat and workflow between systems and surroundings. Thanks for watching.